And today we feel very honored to have Professor David Pan to give us a talk, the AI for IC and the IC for AI closed loop perspectives and the recent results. So Professor Pan is the Silicon Laboratory Endowed Chair at the ECE department of the UT Austin, and his research interests are very broad, include the directional AI and IC interactions, electrical automation, design for manufacturing, hardware security, and the CAD for analog and mixed signal ICs, and emerging technologies. So he has published nearly 400 peer-reviewed papers and 8 US patents, and has served a lot in many IEEE and ACM journal and conference and leadership roles like the ICCAD, general chair, and also he has received a lot of awards, and the best paper awards, the technical excellence awards, and so on. And he's the IEEE fellow and the SPIE fellow. So now let's welcome to Professor David Pan to give us this talk.
Okay, thank you very much, Paul, for your kind invitation. And it's my great pleasure to give a talk today. I hope you guys can all hear me well. Just to confirm. Okay, great. So yeah, today I will talk about AI for IC and IC for AI and their relationship, and also share with you some recent results from my research group. So as we all know, AI is having a great boom and in recent years. And I think the reason behind really is ABC. A means algorithms, and you see, lots of new, neural architectures, from CGAN to RNN to GAN and so on and so forth, right? And meanwhile, right, to fit these algorithms, you do need to have a lot of data. And however, this needs tremendous amount of computation power. And for example, the GPT-3, right, it has many billions of parameters, right? 175, or, it's a huge amount of computing power needed. And that's why we also need to have a huge amount of computing chips, including CPU, GPU, or dedicated ASIC chips for AI accelerations. So, since my research linking this IC and AI together, so just to give you a little bit, introduction about IC design and manufacturing complexities, right? Nowadays, it's easy to have, billions of transistors for a big SoC chip, system on chip, and designing them is non-trivial. For example, usually we have to divide them into several million cells per partition. So let's say you have a billion transistor chips, right? You may have to partition them into many of these smaller blocks. And even designing each of these blocks is non-trivial to meet your timing, power, area, cost, reliability, manufacturability, all kinds of constraints, right? So it could take several days, and you have so many of them. So usually you have to divide and conquer and then integrate them. So it's a really complicated process. And in particular, we are now talking about 7 nanometer, 5 nanometer technology. So that means your feature size, your transistor critical length, and also your wire widths and spacing. You are talking about 10 nanometer or something like that kind of range. It's really hard to, even, first of all, hard to design, right? And also, fabricate them is non-trivial. In the world now, right, there are only 1 or 2 or 3 fabs that can potentially do them, right? So, and also, because the feature size is so small, and usually, in the conventional, this so-called optical lithography process, right? You will generate a mask, and then you will print the mask. But because the feature size is so small, and the wavelengths, the conventional wavelength is 193 nanometer, but the even for EUV, right? So the wavelength is smaller, but to printing them is non-trivial. So you have to do all kinds of so-called OPC, optical proximity correction. Original mask, you have to massage them such that the final image will print pretty much like the original intended image. But it's non-trivial at all, because you may, if you don't do smart things, so you may not look like the original printed pattern at all, right? So, design for many IC design and manufacturing flow is very, very complicated in the sense that, but we do have a pretty systematic way to do it now, right? So usually you have some system level specification at higher level. You want to specify what kind of chips you want, right? Then you push down to architecture, functional, logical synthesis, physical design, and then some mask synthesis, verification, and then you will fabricate them. And then if the chip is working, you are packaging and testing them, right? So this is a very, very kind of brief view of the overall design flow. But even within this, so physical design, as you can see, somewhere in the middle, right? So it has many steps from floor planning to placement to clock tree synthesis, signal routing, and then you have to consider the interaction with manufacturing in the sense that you may need to do some test pattern and make sure, right, the lithography model works, and then use that to guide mask synthesis and so on and so forth, right? So that make sure that they can be printed, right, and fabricated. And if it doesn't work in any of this step, you have to go back and fix them. So the entire process may take many iterations. So years to design a really advanced microprocessor chips, right? So there are so many things you need to worry, from performance, power, area, manufacturability, yield, reliability, security, and last but not least, the design cost. So this is a figure from DARPA program manager Olofsson, and he gave a talk 2 years ago in a keynote. Basically, the red lines here is the total hardware cost, but among these, as you can see, the design cost is also growing like a Moore's law, right? Exponential manner. So even like 5 years ago, right, designing an advanced chip may take $50 million, right? So now you may be talking about $100 million, right? So that's why this is simply not affordable to a smaller company, right? And that's why 2 years ago, DARPA launched an Electronics Resurgence Initiative, ERI, and one of the programs under this 1.5 billion investment is IDEA and Porsche basically want to come up with the next generation hardware compiler. So the main goal is to really cut this design cost so that we have no human in the loop, 24-hour turnaround time. So this is certainly right, very, very ambitious. And so one of the reasons behind is like, hey, we have so much AI advancement, and can AI help? And if so, how, right? So it turns out that indeed AI can help. So that's why today my talk will cover two aspects. One is AI for IC, and another is IC for AI. When I talk about AI for IC, essentially how we can leverage the recent AI hardware and software advancement to enable agile and intelligent IC designs, right? Which people couldn't do before, right? And essentially, nowadays, right, because you have been scaling, right, so advanced to technology node, and actually Moore's law has two aspects there. One is because of the feature size scaling. Another thing is that really due to better designs, right? How to better use those transistors. So if you can do better design, smarter design, that can actually provide equivalent scaling of Moore's law, and also make IC design cost and design automation cost lower. So on the other aspect, when I talk about IC for AI, so essentially, right, how we can design better customized ICs or accelerators so that you can run more powerful AIs, and but more powerful AI not necessarily just means better chips and very power consuming and high performance, but it's also important to have energy efficient and hardware aware ML, right? So very interesting. I think you probably all heard about Moore's law, right? Essentially, the number of transistors will double every 1.5 years or something like that, right? So this is really amazing. It has been true for 50+ years. So there's no other law like Moore's law, right? And that really fuels our modern information technology. But very interestingly, in the last 10 years, the number of machine learning papers kind of almost beat Moore's law, right? So there are so many papers I think I just got some notification today about AI paper that my student got in. And so they are talking about, for all this top machine learning conference, you're talking about almost 10,000 submissions, right? So this is just like unbelievable, right? Anyway, so now you can see if we have this closed loop between AI and IC, right? And if they work together, you have exponential and exponential, whether you say exponential times the exponential or exponential to the exponential. Anyway, these two work together will be really amazing, right? So the rest of my talk will be based on, I'll show you some case studies that we have been working on, right? So on AI for IC, as well as for like IC for AI. So first, let's talk about several AI for IC examples, right? So AI for IC, essentially the key idea is like, hey, how we can leverage recent machine learning, to help design ICs better. And I mean, as I already showed you, right, IC design is a very, very complicated process. And among these so many steps, right, so, here are just some blocks of the IC design process. For example, placement and routing, and then mask synthesis and verification, right? So later I'll show you some more details. But placement, essentially, when you have so many, standard cells, right? So you will have billions of transistors and, hundreds of millions of standard cells or some big IP blocks, right? So where do you place them, right? That is non-trivial because you do not allow them to overlap, and you want to have best timing, power, and so on and so forth, right? After you place them, you have to route, billions of wires, where do you route them, So again, it's really complicated, right? And then you will have probably tens or hundreds of billions of these rectangular shapes, right? Because each wire, you may also need to do some kind of, mask massage, and then ultimately you need to verify whether, it can be printed, right? So how machine learning can help, right? So as I just mentioned here, that can be, used as, to have better tools like hammers and nails, right, to tackle each step, right? And meanwhile, right, so there can also, be a bridge, right, to kind of link adjacent or even kind of bypassing some steps, right? So that you can, for example, while you are doing placement and routing, you can kind of predict the post-mask verification kind of printed image. Then you can kind of know, whether you have hotspot here or here, so that, while you are doing early design, you actually have some kind of smartness to predict what would happen later on, right? So the first case study that I will show is a work that we published at last year's Design Automation Conference, which is a flagship conference in design automation. So the idea is basically how we can leverage deep learning to perform better placement, so which we call DREAMPlace, okay? So we actually have already made the source code available here, and it has been actually downloaded by many companies and universities, right? So first of all, right, what is placement, right? As I already showed you, right? So for modern VLSI design, you have many, macros. This big blocks is called macros, right? And then you have millions, hundreds of millions, or tens of millions of standard cells, right? So this problem is very central to modern VLSI design because, where you place them, you will decide the wires, right? Because there are signals that connects to those. Each of these red dots are a cell, okay? It can be an inverter or NAND gate or whatever, flip-flop, right? But then there's connections between them. And if you found that, okay, you have very long wires connecting, in your critical path, there's no way you can meet your like a 3 gigahertz, clock frequency and so on and so forth, right? So even for modern designs, of course, people would prefer to have bigger flat designs, but because of the limitation of placement, you probably cannot do that. That's why people were, partition them into, each partition with maybe only 1 million, 2 million, or up to 10 million cells, right? And they are very important. And the placement problem is not a new problem, right? So it has been studied since the beginning of VLSI design, right? So you got to place them, right? At the early days, if you only have like 10 transistors, maybe you just hand place them. But now when you're talking about hundreds of millions of cells, there's no way you can hand place them, right? So people have developed the different algorithms. Here is just some very, I mean, there are, every year there are probably, a lot of papers on placement, and it is a very classical NP hard problem. And so there are just also so many things to consider, right? So early days, people have used the partitioning or simulated annealing and so on and so forth. But the state-of-the-art placement nowadays is based on some analytical placement. And so based on some kind of nonlinear optimization, right? So let me show you how kind of a state-of-art nonlinear placement problem looks like, right? So essentially, your goal is to minimize the total wire length, okay? And the reason why we care about total wire length is because total wire length is related with your routability and your performance and your power, right? By the way, right, you may say, hey, I'm also interested in critical paths, right? I want to shorten critical paths when we care about timing, right? But you can use this total wire length. You can also put some weight in front of it so that you know that, oh, if this is a critical wire, you will give it a higher weight. But if you just want to minimize total wire length without any constraint, it's not meaningful, because you may say then, okay, all the cells will be on top of each other and then the wire length is 0, right? But that doesn't make sense, right? So you also want to spread your, those standard cells, those, so that the density at any location is less than certain target, right? So essentially your goal is to spread the cells. And ultimately, you need to also legalize them and to snap them in circuit rows and for power delivery and all this, right? But anyway, I'm not going to the detail here, but we are talking about more like a global placement to get a good overall, placement quality, global placement to begin with. And usually, we will then, from this constraint optimization, we can introduce something called a Lagrangian multiplier or some kind of unconstrained optimization. But then you have to kind of adjust this lambda, and basically, when your density is very high, which violated this constraint, you will give it a penalty, right? And then you gradually introduce some other things so that ultimately you want to minimize your wire length, and ultimately your density is also good, right? So this, although this, I just write this as a very looks very easy, but it's a huge development effort. And if you want to do a state-of-the-art, high-quality placement, and in like EDA companies like Cadence and Synopsys, a placement team can easily have 50 people or something like that, right? But even for academia, to develop a high-quality placement engine can easily take a year, right? Because this area is heavily studied, and to really push the state-of-the-art, even by a few percent, is non-trivial. Okay, so of course we want to have a dream placement engine, right? So what is a dream placement engine, right? You want to have the best quality of results. You want to be really fast, right? And because this placement is at the center of the entire design flow, right? If it is very fast, you can afford to run many iterations, right? Remember previously, right? If you go to the latter step, you may have to go back, right? So that means you have to run your placement many, many times. And also, we want to have low development effort. For example, let's say, previously we developed an academic placement engine take a year, and whether you can do it in a month or two, right? Wow. Then graduate students, right, while you are even doing a master study, can play with it, right? And then you want it to be extensible in the sense that, right, so if later on you develop the new algorithms and acceleration techniques, it's very easy to, kind of upgrade it to the next generation instead of throwing the original one and rewrite a new one, right? So basically, right, so, whether we can do a 10 million cell designs in minutes, right? This is like now it takes several hours, right? So actually our kind of insight from this advancement of recent deep learning hardware and software advancement. So in terms of hardware, we know that the GPU, has been really, very, very successful and widely used to do all these neural network kind of applications. And meanwhile, right, so the deep learning toolkit this is from hardware perspective, right? And by the way, there's also dedicated hardwares like Google TPU and all these neural accelerators for ASICs, right, for neural like AI type of applications, right? But on the software aspect, there are a lot of open source, right? For example, TensorFlow from Google and PyTorch from Facebook, right? Have an infrastructure which actually, many millions of programmers probably contribute here, right? And they make it open source. So our actually strategy is like, hey, can we actually have we actually found that there's a really nice analogy between the nonlinear placement problem with a neural network training problem. So then we can greatly leverage deep learning hardware, in particular GPU here, and software toolkit, for example, PyTorch that we used, so that we can actually allow to have really high parallel and acceleration while getting state-of-the-art results. Okay, so let me show you the analogy between the neural network training and the placement. So as you can see, right, so when we do training, right, usually you have some data instance, and then you have for the propagation, you compute the errors through your neural network, right? And then inside that, you have certain weight, and you will find, based on your error function, you do back propagation with respect to the weight, and then you can kind of, adjust the weight. And after so many iterations through this forward and backward propagation, you have a trained network, which minimize your, error function, right? And meanwhile, right, to avoid overfitting, so you may introduce a regularization function so that you don't do overfitting, right? So this is a typical flow to train a neural network. Okay. Actually, very interestingly, if you look at the placement objective function, we want to minimize the wire length and subject to certain, subject to the density constraints, right? So it actually looks very similar to this form, and we can then actually have an analogy between placement and neural network training. We basically say, hey, our net instance or these net connections are my data, and my goal is to minimize wire length. So then I will set my wire length to be goal is 0, right? But that's a mission impossible. But still, you will have error function. But then your error function is the ultimate wire length. And then what is your weight? The weight actually is the XY location of each cell that you want to place. And then through forward propagation and then backward propagation, and similar to this, then we can actually compute the ultimate weight, which is the XY location, which will minimize wire length and subject to some density constraints. All right. So that's really nice. And because of this, right, so to develop a new placement engine, like in the past, to develop a placement engine takes a tremendous effort, and people have to write new solvers and nonlinear solvers, conjugate gradient, and all these kind of things. And then you have to see how to adjust your lambda, what is the schedule, and all this, right? But now, to develop a new placement engine, it actually we can significantly leverage those mature and highly optimized deep learning toolkit. So which are available in Python or CUDA library. So for example, those nonlinear optimizers and the gradient computation, etc. Right? So what we need to do is to have a new placement API, but we do need to have our own customized calculators, operators for wire length computation and density computation. Right? But because of the time limit, right, I probably won't show the details. But essentially, right, so by the way, because of state-of-the-art, nonlinear placement usually use another solver called Nesterov. So we also actually try to match that. And we implement our own nonlinear optimizer, Nesterov, right? But actually, we found that later on we can use the other nonlinear optimizers, which is already available, so we can get similar results, right? So now, let me just, I want to show some other details, but let me just show you some results. We compared the DREAMPlace, our placement, with a RePlace, which is a previous state-of-the-art academic placer, with many CPUs, many cores, and we only use one GPU to do our placement. But we will have a single CPU to read the placement and so on and so forth. So we found that compared with this versus our placer can get the same quality of results because we try to match the placement engine algorithms. And but we got like 30 to 40 plus x speed up. So this is really nice because in particular for very large industry designs that we collaborate with NVIDIA, right? So, if you are going to run it by the previous placer, it pretty much like crashed, right? And even we kind of projected the runtime, it will take at least 3 hours. And our algorithm actually, our DREAMPlace finished within 5 minutes. And with a newer version, by the way, we actually can get it done within a minute, right? Because it's really fast, and the result is also amazing. So looks like basically, right? Remember at the beginning we have a bunch of dreams, right? So best quality results, ultra fast, and the coding effort is also low, and then we can also extend it and also innovate to other algorithms, innovations, and accelerate her, to take advantage of all these accelerations. Right? Sounds like our dreams really come true, right? Actually, we can also dream bigger, right? Especially here, I think we have a lot of graduate students. When you do your PhD level or even master level thesis and research, you want to dream big, right? So you want to make an impact of your research, right? So with this DREAMPlace kind of framework, right, we can actually now use new solvers, right? And which, the machine learning community have been doing a lot of study in this. And also we can consider new objectives, for placement, for example, not only just wire length, how about the routability, timing, and so on and so forth. Actually, in our journal version of this DREAMPlace, we have already showed some of these results. And meanwhile, right, there is also multi-GPU, distributed computing, mixed precision in the acceleration, AI community, right? So we can probably take advantage of that. And also, here we showed for placement, right? But there are many, many other important CAD problems, such as gate sizing, floor planning, and so on and so forth. Can we also use DREAMPlace-like methodology for that? So that's actually an open question and challenge to you guys. Right? All right, so now let me show you another case study. This is effort that I'm leading at UT Austin as part of the DARPA ERI and effort. So the goal here is to do a machine-generated analog IC layout, which I call it magical, right? So again, we also have made the open source available here. So the DREAMPlace, as you can see, focuses on digital IC, right? We have we are talking about the tens of millions of standard cells. But for IC, analog IC, that's a totally different kind of world, right? So people are not talking about the millions of cells, not even hundreds of thousands or thousands, right? So oftentimes they may only have hundreds of transistors, right? But they are really hard to be done automatically, and there are design automation effort for analog IC layout, but it's not successful. And even now, right, analog IC design is still mostly manual, very tedious, very error-prone. But analog IC design, are very important, right, for all the future 5G, 6G, or this healthcare, wearable electronics, right? So, what our goal for Magical is to develop a fully automated analog layout system, leveraging both human intelligence, from human experienced designers, right? Analog IC designers also often, think themselves as some kind of magician. They have some black magic. Oh, they should do it this kind of symmetrical way, or this way, the other way, right? So they feel very proud of it. But again, it is very, error-prone and need experienced engineer, right? So if basically our goal is to leverage that experience, but meanwhile intelligence, but meanwhile we also want to have machine intelligence, because computer can scale, right? And also with AI, and maybe we can also leverage human experience and put it back into our engine, right? So we have already got a lot of very exciting results and some publications here. So let me give you an overall overview of Magical. basically, Magical is very ambitious, as you as actually challenged by DARPA, right? So they want to have a 24-hour no human in the loop, right? So essentially, our input netlist is just some circuit netlist, and with DRC rules and PDK, right? And then the output is kind of LVS clean and DRC rule, no DRC clean, GDS2 layout. This is, and then intermediate process, we do everything from layout constraint generation to placement and routing. And we also have a device generator based on the netlist will generate the P cells, the parametric cells. Because of the time limit, I won't show all the details, but basically, right, we have heuristic algorithms, analytical algorithms, and also some machine learning algorithms, pattern matching, and so on and so forth, right? So you can refer to our Magical website for the also the the GitHub, right, for the details. But we have got some very exciting results, right? So here's a simple two-stage miller-compensated OTA designs, and this is a manual layout which my collaborator Professor Nansen has already tapped out, and in TSMC 40 nanometer. So and this is a manual layout, and this is our Magical layout. And as you can see, they look very differently, right? But if you look at the all these performance metrics from CGAN to CMR and so on and so forth, right? So our Magical actually is doing a fairly decent job, and you can see we can do all this symmetry very well. And in terms of compactness is also very nice. But in terms of the effort, right? This for a human designer, a PhD student, right? Experience. So it may take a week, right? But for us, running Magical, it only takes seconds, right, to generate the layout. And we can also tune the parameters so that we can generate hundreds of thousands of different layouts. And actually, we even released a benchmark, and which then we can also do post layout simulation, and then build a learning database so that we can actually study different kind of layouts that the human designers may not think about, right? So that actually is very interesting. So actually, we not only did this kind of component level, and recently we also tapped out a very advanced kind of ADC systems. So as you can see, this is the third order continuous time delta sigma modulator. And so we actually did all the layout automatically by Magical. And compared with the schematic, the Magical actually is doing fairly well. And so we are very excited about this. All right, so now let me also show a third case study for AI for IC. So it is kind of linking the design and manufacturing, which I already mentioned before, right? So basically, right, we want to get an end-to-end lithography simulation. For example, right, originally, right, let's say I have a design which looks like this. I want to know whether it will print like this or this, right? Depends on what kind of mask, right? So usually this is a very, very expensive process, right? So as you probably know, right, usually during the circuit design, you were, you design it and then you will make certain mask. Ultimately, it's a bunch of rectangular shapes at different levels, whether it's transistors or wires and so on and so forth, right? But it has to go through very expensive, area image simulation and photoresist, and to simulate even a 2 micron by 2 micron area, it could take a minute, okay, using advanced lithography simulators, right? So to use that to guide design is impossible, right? So that's why we want to actually even before we are trying to get a detailed shape, right? So there are actually a lot of research people have been doing to say, hey, if I give you certain kind of layout, whether there is some hotspot there, basically it cannot be fabricated with good yield, right? So this problem actually, we actually studied this more than 10 years ago. We published this paper, which is among the first to use machine learning for lithography hotspot detection, okay? But at that time, it's not deep learning. We are actually, use some support vector machine, right? And but later on, right? So this actually triggered a tremendous amount of interest, and then people also use the deep neural network, and also a lot of transfer learning, because when you're talking about advanced technology nodes, you may not have that many learning data, right? So how do you use the current technology model together with some new technology learning data, right? Anyway, so there are a lot of work people have been doing on this. But what I'm talking about today is actually even a harder question. Basically, we not only want to know whether it is a hotspot or not, right? That is a binary decision. Actually, we want to even directly predict the printed image, right? So basically, we want to know, if you give me some input, what is the final printed image looks like, right? So this one is definitely a very, very hard problem. But we actually got inspired by the recent advancement of GAN. For those of you who have been following, machine learning community work, so GAN is really, really, powerful, and so it's actually very, very powerful. Basically, I won't go into details. It has two neural network contest together, right? So one is generator, another is discriminator. So ultimately, the generator will produce image, and then the discriminator will say, hey, this is fake, let's say fake $1 bill or not, right? And stuff like that. Through back and forth, at the end, the generator can generate some fake US dollar, for example, $1 bill so well that the discriminator probably cannot tell, right? This is GAN. And then you can also do something called conditional GAN. It can take a picture in one domain and actually translate it into another domain. Right. Anyway, I won't go into details. Here are just some popular, for example, a black and white flower. You can actually make it into color flower, right? So what we actually do in this is that we actually, let's say this is like a mask, and with, for example, this is some pattern you will need to print, okay? And usually to print those kind of patterns, you also need to even, insert some kind of assist features, right, to make those pattern print, right? So it's a really complicated process. So, as I mentioned, right, if you do lithography simulation to get the final printed image for this guy, right, for this green vias, it will take a lot of effort. But then, if we can cast it into like a CGAN problem, to do image translation, it actually will be, so direct image translation from here to this, right? For this image that you are interested in knowing what is the final printed image, right? Because this is a critical feature, maybe a transistor or maybe a via, right? So I won't go into details, but basically we have a bunch of training data set, right, with the input image and output patterns, right? So we'll build, we will have generator, discriminator, right? And I build this CGAN architecture. And again, I won't go into details, but yeah, this paper was published in last year's DAC, and was nominated for Best Paper Award. So, so interestingly, we found that actually it kind of this process actually during the training, it can the final image, let's say after epoch 80, looks really close, right? So compare with the image that we were obtained from detailed simulations, right? However, compare with rigorous simulators, right, which are based on physics, chemistry, and all the nasty stuff, right? The LithoGAN direct image translation is over 1,800 times faster than those simulators, with acceptable errors in when we discuss with industry, right? So maybe you have 0.1 nanometer errors, maybe here, there a little bit, right? But they will say, that's good enough, right? So with this, actually, will be really, really useful to bridge the entire gap between design and manufacturing. Right? So we further actually, use the GAN to do so-called SRF insertion. What is SRF, right? It stands for Super Resolution Assist Feature Generation. Essentially, as I just mentioned, right, to print those kind of image, you need to also generate a certain kind of super resolution assist features to help these red patterns to be printed reliably. And again, how to generate this kind of black support image is a very, very, very expensive process. If you are going to use models to guide it, and then you want to kind of flip and say, hey, should I put a black dot here, 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 and there, and so on and so forth, right? So again, we can use GAN to do it, and it can be hundreds of times faster compared with the model-based SRF insertion, but we still can get similar quality of results. All right, so now let me actually spend the next maybe 15 minutes, 10 minutes talk about some IC for AI aspect. So to close the loop, right? So far I have talked about AI for IC, right? But once we have more powerful IC, we can go back and help to run AI faster. There are many, many works, from industry on this already, right? To have customized the IC for AI applications. Okay, so but all these are based on conventional transistors and electronics, right? So actually, it turns out that you can also have another paradigm of thinking to do the computing, not only based on CMOS transistors, but based on the photonics, right? So this is actually a paper published from MIT in 2000, actually 3 years ago in Nature Photonics. So actually, after they published this paper to allow optical deep learning, there are quite a few startups already on this, right? 2 from MIT, and I heard there are quite a few from others, right? Altogether, probably close to 10 startups in this domain. So what is the key idea behind the MIT's nanophotonics paper, the first paper on this idea? So the key idea is like we know that when we are doing deep learning and optical neural networks, right? One of the key operations that we need to do is to do a matrix multiplication, right? But actually, instead of doing like a digital and you have to compile it and using your whether it's GPU or TPU to do this matrix vector historical array to do this kind of multiplication. Optical neural network actually has a light input, and let's say you can imagine you have light comes in through certain kind of optical array, light comes out, and you can say, hey, let's encode the vector as my input light intensity, and the matrix you can kind of implement using the middle part, which is some kind of MZI array. Don't worry about the details, right? But then so basically the key idea is that, like, once I configured this optical array properly and as a certain kind of matrix-like thing, and then the light comes in, and then you have matrix. Then the output is directly vector. That is matrix vector multiplication. So in that sense, it's actually analog computing directly, based on your physics and optics to do the computing for you. All right. Of course, after it is computed, you have to detect the light intensity and so on and so forth, and then maybe you have to convert it ultimately back to the electronics domain. But if you can stay in this domain longer enough and also do all this key computation, basically this kind of optical neural network computation takes really low energy and when configured, right? However, there's some problem. What's the problem, right? The problem is that the area is bulky compared with CMOS, because when you're talking about CMOS, you are talking about like a 7 nanometer, 5 nanometer nowadays, right? For the most advanced technology. But the for optics, even nanophotonics, actually we are talking about the micron, right? So the area for each of these like MZI array or those optical devices is much bigger compared with CMOS. So that's why in this aspect, so we have been working a lot on this optical neural network architecture, how to make it reduce the area without losing the accuracy. So this is the original MIT architecture. So what they do is that they will do software training first. They get a weight, and then they will do singular value decomposition. You get a U and this V matrix, and then you will use MZI arrays. You will map it to hardware implementation. All right. However, we actually propose some new architecture instead of doing software training followed by hardware implementation, our idea is that we are going to do a software and hardware co-design. Again, due to time limit, I won't show the details, but essentially through this hardware and software co-design, instead of you need two big matrix, okay, we only need one big matrix like this, which is a unitary matrix. So that means we can save area by up to 50%. But we found that, in terms of accuracy loss, we don't have accuracy loss. And actually, it is better for noise robustness because, you have less devices, and so they will interact less. Right? So this is actually some result that we have shown. We show that you got 15 to 38% of area reduction in terms of MZI, and with no accuracy loss. And now, we also actually further improved the previous architecture. The previous one, is still based on something called MZI. MZI is a kind of more general like implementation for any matrix vector product. But we found that we also actually there's another kind of circular matrix multiplication, which is a specialized matrix. So we found that actually from a machine learning community, there are people published that shows that with only circular matrix, you actually can do a lot of machine learning tasks very well. So, and very interestingly, we found that with circular matrix multiplication, we can have a new FFT-based architecture to implement it. Essentially, we are going to do optical domain FFT and inverse FFT, right? So, and they implement it directly through coupler and phase shifter and attenuator and so on and so forth, right? Without using MZI. But by doing this, we can reduce the area, not only just by previously we only reduced it by maybe 30% right, area, but now we can reduce the area by 4x or 3.7x up to, right? And we can also reduce the latency and the energy efficiency. Compared with the original MIT paper versus our newer ones, right? So, you have a factor of almost 10 reduction in terms of latency, and also energy efficiency is 10 times better, right? So, another case study that we have done, this is just published at this year's Design Automation Conference. And so the previous two, optical, neural network is mostly only used for inference. That means the weight, once you got trained, right, the weight is fixed, right? But it's also interesting to do the training as well. But when you are doing training, right, so you usually need to have a forward propagation, but also backward, right? But backward to compute the gradient is actually pretty hard using optical device directly. So that's why we proposed the stochastic zeroth order optimization. Okay, I won't show the details, but ultimately, so we can, do, much better compared with the previous approach. And one thing that I would like to mention is that when you are doing on-chip optical training, it actually can take care of the built-in kind of signal, or crosstalk variations very well. In the sense that, okay, usually, right, so your optical device will be, susceptible to thermal variations, right? But those thermal will actually impact your device. And there's in general, right, if you have to really consider it during your training, you have to measure the, thermal profile, and then, adjust your model, and then ultimately, modify your neural network, right? But because now we have on-chip training, everything is done in situ. So that means, anytime you have higher temperature, your device will measure that, it will directly respond to that higher temperature, right? So then we can actually directly respond to that. So it has built-in variation handling. So that's why, as we can show here, so basically, right, originally, if you just do software training and then map it to hardware, you will actually have like a 5% or 6% accuracy drop, right, in terms of your trained model. So, however, since this new flop, right, is hardware and the software kind of on-chip training. So we will not have any drop in terms of voltage, in terms of the accuracy. So and that's why it is actually very, very nice. And when you can do this kind of on-chip training. Right? All right, so just to give you like this, for the very brief overview of this kind of more optical IC for AI aspect, right? But I hope you get a kind of feeling how it can be done. Just to recap, so I have shown you the AI for IC, right, for different aspects, from placement to lithography modeling, SRF, and also the magical for analog design, no human in the loop, right? So, and in terms of IC for AI, I showed how to build ultra fast, light speed, and ultra energy efficient optical neural networks, optical neural accelerators. And so how to do software and hardware co-design and with these different new architectures. And we have also even tapped out optical chips based on our FFT, and we are still measuring it, right? So to conclude, right, so really, as I already showed you, right, the AI and IC should have a closed loop and interaction. On one hand, better AI algorithms can help designing better ICs. And of course, if we have better IC and AI accelerators, it can allow you to run AI algorithms significantly faster. So if they keep on working together with these two exponential that I showed, right, for Moore's law and the AI, so I think the future is really bright, and there's really a lot of research opportunities, right, in this area. So with that, I'd like to conclude. And first of all, before that, I'd like to thank all the support collaborations from different funding agencies and collaborators, and also, of course, students and who do the real work, as well as my collaborators here, right? So, all right, thanks, and let's have some Q&A. Right? Thank you.
Okay, thank you, Professor Kan, for your very excellent talk. So, if students have any questions, so you can type in the chat or in the Q&A channel. Yeah, yes. So they input their questions. So I have one question. So for your slim ON architecture, so why the original MIT work and your work need to do the SVD? Can we directly use the vector matrix multiplication to do that, or because the optical network, the optical device, they must to use this SVD property to perform the MVM? Oh,
well, okay. So in the original MIT architecture, right, what they have is that it is for inference, right? So it has a chain network, and once you already trained it, right, so you will then have a weight matrix. Then you do a decomposition, because this kind of MZI array cannot implement any weight, so it has to do a SVD, so that this is a unitary matrix. U and V is a unit. Oh. So it's not any arbitrary matrix, right?
Oh, okay, I understand. Okay, right. Thank you.
Because of the when you are trying to build this kind of optical kind of array structure, right? So using MZI, so this kind of matrix, right? While you are formulating, it can only be unitary matrix, right?
Okay, thank you.
And but the thing is that you have unitary matrix followed by another this and followed by this. This entire thing becomes your big original matrix, right?
Yeah.
You got it? Yeah.
Thanks. Yeah.
So for our sling architecture, right, basically, we will say, oh, we are not going to use this kind of architecture. And then, okay, so when we are doing this kind of software and hardware co-design, we cannot handle any arbitrary matrix. Not any arbitrary matrix can be implemented using this. Okay, so that's why we will do software hardware co-design. We will try to find a matrix W that can be implemented like this, right?
Oh, okay.
So because as you know, right? So the matrix is not unique, right? People even do a lot of trimming and kind of right stuff like that, right? So So you can do another way, and it will then still, in terms of accuracy. So compared with original inference, right? Original, let's say inference one, you get certain metrics, right? You implement like this. Now we will do a software hardware code training, and then we got a matrix, and then we implement it. So essentially, this wet matrix and the implementation is together, right?
Yeah, yeah.
Make sense?
Yeah. So okay. We have some questions coming. So
yeah.
For the eye-opening sharing, the first model, minimizing the wire length and maximizing the module size is straightforward but less accurate. What other parameters did you also put into your model? Can you please give several more key considerations?
Sorry, let me try to see. So let me try to see if I can see the question.
Yeah, you can see that in the Q&A. Yeah.
Yeah, hold on just a second. I cannot see it right now. But anyway, so is this the question regarding the placement? Is that right?
Yeah, I think so.
Okay. Somehow I don't see the chat window. But anyway, let me answer. Oh, okay. Let me see what. Oh, okay. Now I can see the chat window. Okay. Yeah, because I was in the full screen. So yeah, in terms of the, let me read the question again. So, very few found. Oh, okay.
I think so that question is not in the chat window; it's in the Q&A. Yeah.
Oh.
Q&A window.
I see. Okay. All right. So we have too many windows. Okay. Thanks for the eye-opening. Okay, the first model, minimize the total wire length and maximize modulus. Okay, so no, okay, so you can still see my mouse?
Yeah, we can see that. Yeah.
All right. So usually when you are trying to minimize the, the objective function for the wire for the placement is you want to minimize the, the connections and the wire length, right? So that's the objective function. But meanwhile, you don't want, for example, in this animation, right? You can see that if you don't, in this animation, you can, if you don't do it properly, all the cells may be on top of each other, then they claim, hey, my wire length is 0 because the wire length is between the cells, right? But that's not meaningful. And then this question is about maximum modular size. No, we don't want to maximum modular size, right? Modular size is fixed, right? For example, each of the macro and also these cells, right? Some of the flip-flops, some of inverters, their size has already been fixed, right? So yeah, it's just minimize wire length. I don't know whether. Yeah. I'm not sure what this question. I think the question is from Yu Xuan. Right? So the maximum module. I mean, no, we don't want to maximize modular. Right? First of all, right? So the I don't know what do you mean modular, right? So modular is for each macro, the size is already fixed, right? And our goal really is to try to minimize the wire length. But sometimes, we not only minimize total wire length, but we also minimize kind of path wire length for critical paths. And you can actually adjust the weight in front of the wire length to minimize it. So. Okay.
Yeah, we have other questions in the chat window. Yeah.
Okay, let me go to the next chat window. So this question is from Murali. And he asked, considering that there are very few foundries and fewer on 5 nanometer, how open would they be with making this process easier? How open? Wouldn't that hurt their business? Of course, no foundry will open their process. We are talking about hundreds of millions, billions of dollar fabs, right? So they will not be open. But okay, so let me. I guess your question is that in terms of the simulations, right? So, I mean, even this S-Litho, right, from Synopsys, right? So they need to fit the whatever certain parameters from the foundry, right? So this kind of parameters, is secretive, right? So they won't tell you what is their secret source, right? But there are some open literature. You can make some assumption, right? So what we are working on here is a core, even this S-Litho or those kind of OPC, right? From the EDA companies, right? They are not fabs, right? So they don't have those secret, parameters. But you can make a reasonable assumption, and those companies buy their software, and then once you are inside the fab, they can tune and use their own really secret source parameters, right? Okay, so in that aspect, right? So that, of course, we want to make that open. But in terms of the neural network, and if it is trained with some synthetic data, right? Essentially, we generate some synthetic data ourselves, right? We do have access to the S-Litho or those kind of lithography simulators. They are very slow, but hey, if we just launch many parallel runs, and we can collect thousands of this kind of learning data, right? But our learning data is not based on the real, fab data, right? Because we don't have access to that. But we can make certain assumptions, and we actually collaborate with some of our collaborators and make some reasonable assumption, right? So then we can start. But the methodology, of these kind of learning models, right, will be applicable not only to synthetic, but could also be applicable to real data. But then maybe you have to retrain it or adapt it, right? That's why I also mentioned something like transfer learning, right? So maybe you train it for some technology, and maybe with a little bit more training, with the real data, right? You can actually adapt it to the real industry scenario. Okay. So, well,
yeah, and I think there's another question in the chat channel.
Right. Okay. So another question that maybe you can help to pick what questions, right? There are a lot of questions.
Why are less TPU cores used in the design of, let's say, a GPU? What does this question mean?
TPU is Google's, right? So it's their own like a systotic array, right? So that's very different, right?
Yeah,
okay. A TPU is an entire, you can think about it as the entire GPU, right? Okay. Yeah. Okay. Let's move on to the next question.
Yeah, I think.
There are some questions in the Q&A, right?
Okay.
So this is a question. Let me see.
Yeah, there are several questions in the Q&A.
Oh, okay. So I can answer Li Yin Huang's question, right? He's saying basically, right, he's interested about magical, right? So there are also other auto layout tools available online, like Cadence, but the performance is not so ideal. Even after the auto layout, we still need to manually correct on lots of things. Yeah, that's the thing, right? So yeah, especially for analog layout, right? So yeah, the auto layout is not ideal. That's why we started this magical effort. We hope that after magical, it will be ideal. And also we make it open source, so you can if it is not ideal, right? So you can try to tweak it, right, for your goal. So then the next question from Ling Yi Huang. So I'm wondering about what's the main advantage of magical compared with those of available auto tools. Yeah, the available auto tools, right, from Cadence Synopsys, they don't do analog, right? Or even if they do, right, it's very, not very good yet, right? So I'm not saying that magical is very good yet. I mean, it's still ongoing research. So actually, there are two DARPA projects in the IDEA program, which actually funded this kind of automatic analog layout. I'm leading one, magical, and Professor Sachin Sapatanecker from University of Minnesota is leading another one called Align. So I guess this is a very hard problem, right? So people have been trying to work on it for decades, but not yet being adopted, right? So we hope that through human and machine intelligence together, we can really have a breakthrough. But I think one thing that I'm really happy and proud to announce is that, as I showed before, right? I think people have never done that kind of thing. For entire, ADC, we can, have a push button, right? And no human in the loop, we can generate really this kind of nice layout. And as you can see, compared with schematic, our performance is really good, right? Very competitive. Okay. But there's still a lot of research to be done, okay? And to cover all different circuits, all different technologies, I mean, so there's still a lot of work to be done. Okay. Maybe one last question from actually Jikun Peng. Okay, same last name as me. All right, so for printed image prediction, you told in case study 3, because I did some research on SLA 3D printer, is this technology similar to open source SLA technology? Like we get to the scale of object from GAN? Thank you very much. Well, yeah, GAN is a very powerful technique, right? So essentially it's to do, as I showed before, right? It's to image translation, right? I think people have used the GAN not only to generate a fake, images, and you can use GAN to generate how do I say, Picasso-like pictures. And even you have a photo of yourself, you can kind of add some flavors to it, right? And you can generate fake faces, which look so similar to real people, right? So GAN has been really widely used to do all these tasks. And we are just adopting it, but to the, lithography kind of domain. And I actually call it modified image translation, because actually, the scale is different. As you can see, this one, even it is 256 by 256, but this image is much bigger. So here, I'm only caring about the image, for this green kind of view, right? So I have to zoom in, because I ultimately need to, get the detailed shape, right? So the resolution needs to be very high. So, so anyway, so we actually, yeah, the principle, this basically is the principle of the GAN and the CGAN, right? But we have to do some customization, right? So yeah, the principle, of GAN is very general, right? Okay, I guess that's all the questions.
Thank you very much.
Oh, you are very welcome, right? So thank you for your invitation, and thank you for listening to my talk. And I hope you have you stay safe, okay, and healthy. Take care. Okay. Any other? Oh, there are still a lot of folks here. Okay. All right. So thank you, Paul.
Thank you, Professor Pan. Thank you.
Okay. Thanks. Bye.
Thank you. Thank you, everyone. Bye.